So just as a quick reminder, any function that looks generally like this, that's kind of got this upward parabola shape to it, this is concave up. Anything that's shaped like this is concave down. Even if it's just like barely going up like this, that is still concave up, right? Or barely going down, that is still concave down. All right. It doesn't have to be as steep as these ones are. Right? Just so long as if I followed this same trajectory, this same curvature of it, I'd end up with something that eventually looked sort of like that. Right? Concave up and concave down. So let's think a little bit about a function that's concave up. So let's take a look at this function right here that we've just drawn that's concave up. And let's think about the slopes of the tangent line to that function. So what's the slope right there of the tangent line? I know it's not perfect, but what's the slope of that tangent line there? Just take a guess. Negative something, right? Negative, what do you think?
-4.
Great. All right, -4. All right. Then let's say over here. Oh, that was really bad. Let's say like over here. Pretend that's a tangent line. What's the slope there?
-2.
-2. Sure. Okay. What about here?
Zero.
Yeah. All right. And then over here, maybe 2, and then maybe. Oh, that was bad. Over here, maybe 4. So what's happening to the slopes of the tangent line to this concave up function as I move from left to right?
The slopes are increasing by 2.
Well, yeah, and they're increasing by 2 in this particular case, just based on where we drew these lines. But overall, they are increasing. And remember that the slopes of the tangent lines represent the derivative. And so this function, which is concave up, has its derivative increasing as we go from left to right. Like if I draw a bunch more in here, we would have had one where it was 1, and one where it was 1.5, and one where it was 1.9, and all that. Right. But the important thing to note here is that these slopes are increasing, meaning the derivative is increasing. And what about on the concave down one over here? Starting at some positive value like 4 and going to something like, I don't know, that maybe looks like 1 now, and then 0, and then like a -1, and then like a -4. And what's happening to those slopes, or to the derivative of this function?
Decreasing.
It's decreasing, exactly. So if the derivative increases on the interval, the function's concave up, and if the derivative decreases on the interval, it's concave down. Well, if y prime is increasing, y prime is just some function, right? Y prime, this function is increasing. What can you tell me about its derivative?
It's positive.
Right. If a function is increasing, its derivative has to be positive. And if a function is decreasing, what can you tell me about its derivative?
Negative.
It's got to be negative. And so we should be able to use a second derivative test here to tell us when the function is concave up and when the function is concave down. So anytime our second derivative is positive, that tells us that the derivative is increasing, which tells us that the function is concave up. Anytime the second derivative is negative, it tells us that the derivative is decreasing, and it tells us that the function is concave down. Good or no?
Good.
All right, so let's write concave up, y prime increasing, y double prime positive, and concave down, y prime decreasing, y double prime negative. All right. Cool. So that will be the rule that we're going to use when we try to determine the concavity of functions. So we're going to start with the nice easy function again, y equals x squared. You should, without doing any calculus, be able to tell me the concavity of y equals x squared, right? That function is concave up for its entire domain, right? So let's see what the second derivative is. So y prime is 2x, right? And y double prime is
2.
2. 2, no matter what x value I plug into 2, 2 is still 2, right? 2 is greater than 0 for all values of x. And therefore, this function is concave up for all real numbers from negative infinity to infinity. Easy enough?
Yes.
Perfect. All right. Let's take a look at the concavity of the function y equals 2 plus sine x on the interval 0 to 2 pi. So what are we going to need to find that?
The first and second derivatives.
We will need a first derivative followed by a second derivative. Exactly. So let's find our first derivative. The first derivative should just be
Cosine x.
good. And our second derivative should be
negative sine x.
negative sine x. So we are now looking for when is negative sine x positive and when is negative sine x negative. So in order to figure that out, we should probably figure out when this second derivative is equal to 0, or perhaps also when it's undefined, because those would be the only times when it could change from being positive to negative, right? If we had a discontinuity, it could jump from positive to negative, or if it went through 0, if this equaled 0, that'd be a time when it could change from positive to negative. So just like with the first derivative, we looked for when it was equal to 0 and when it was undefined, we're going to do the same with the second derivative. So on the interval from 0 to 2 pi, we're going to put our endpoints of our interval, even though they're not closed endpoints, just to make sure we don't test outside of that. And when between 0 and 2 pi, does sine x or negative sine x equals 0?
Zero and pi.
Right. We've already got 0 and 2 pi, so we'll put on the pi. So now this is a sine chart with our second derivative. So if I plug in something between 0 and pi, let's say pi over 2, what's the sine of pi over 2?
Root 2 over 2.
That'd be the sine of pi over 4. But we can use that. That'll work. Let's say we pick the sine of pi over 4. That'd be root 2 over 2, and then it's negative, which tells us that on this interval, the second derivative is negative, which tells us that this is concave down on the interval from 0 to pi. And what about pi to 2 pi? If we pick something between pi and 2 pi, we know that sine in the third and fourth quadrants is always a negative number. Right? Doesn't matter which value I pick. Suppose I pick 3 pi over 2, right? Sine of 3 pi over 2 is -1. So we have negative 1, which is positive, telling us that this is concave up on that interval. And so we would write this out as concave up from pi to 2 pi and concave down from 0 to pi. And you'll note that this time the College Board does it right on the points that are real number values that are included values, like pi is an included value. We still use parentheses like we should. Any questions on that? Are everybody okay with that?
How did you know to put pi in the middle? I missed that.
We were looking for when our second derivative equaled 0. So we knew that sine x or negative
Okay.
x equals 0 at 0 pi.
Thank you.
Yeah. All right, and so here we've got 2 plus sine x. That was our original function, right? So from 0 to pi, which is right around there, 3.14, it's concave down, right? And from pi to 2 pi, right about there, it's concave up. Good or no?
Good.
All right. So let's take another one of these equations and see if we can add a little something to it. We're going to talk, I think I mentioned the term a point of inflection. A point of inflection is a place where our function has a tangent line, so our function exists, and where the concavity changes. So just like a local max or a local min is a point that's defined on our function where the function goes from increasing to decreasing or decreasing to increasing, well, a point of inflection is a point on our function where the function is defined and it goes from concave up to concave down, or it goes from concave down to concave up. So we're also going to be looking for all of these points of inflection. So in order to find the points of inflection, we need to find the concavity. And in order to find the concavity, we need a
Derivative.
yeah, we need a first derivative followed by a second derivative. So y prime, well, let's see, y prime is the derivative of this. This is e to the u, right, with u equal to negative x squared. So that ought to be e to the negative x squared times the derivative of u, which is negative 2x. Everybody good with y prime?
Yeah.
All right, and then for y double prime, we need to use the product rule. So we've got e to the negative x squared times negative 2x. So we'll do e to the negative x squared times the derivative of negative 2x, which is negative 2. And then plus our negative 2x times the derivative of e to the negative x squared. Well, we already know the derivative of e to the negative x squared, right? It's e to the negative x squared times negative 2x. Everybody good with that or no?
Yes.
Okay. And so to simplify that down and figure out when it's equal to 0 and when it's undefined, what do we need to do?
Factor out the e to the negative x squared.
We got the e to the negative x squared. That's going to leave us with a negative 2. And then plus, looks like plus 4x squared. Yeah. So when does that equal 0 and when is this undefined? First off, can I square any number and then make it negative and then raise e to that power?
Yes.
And I plug any number, I can plug any number x into e to the negative x squared, and I should be able to plug any number x into negative 2 plus 4x squared. Both of those will just give me a number. So there's never an undefined, so we'll say never undefined. Okay. And so now we just need to set both pieces of this equal to 0. E to the negative x squared itself doesn't ever equal 0, right? But negative 2 plus 4x squared does, right? 4x squared equals 2, or x squared equals a half, or x equals plus or minus 1 over root 2. And so we will put those two values, negative 1 over root 2 and positive 1 over root 2, onto a sign chart for the second derivative. Good or no?
Good.
All right. What's a nice easy number between negative 1 over root 2 and positive 1 over root 2 that we can use to check?
0.
Yeah, 0 seems like a good one, right? And e to the negative x squared, no matter what's going to be positive. So really all I'm looking at is the negative 2 plus 4x squared. So negative 2 plus 0 is just negative. So we're going to be concave down in between. and then something more than 1 over root 2, like 1,000, this e to the negative x squared is still positive. Negative 2 plus 4 times 1,000 squared, definitely positive. And then something less than negative 1 over root 2, like negative 1,000, is going to give me positive times another positive. So we're going to be concave up. And so how many points of inflection do we have?
2.
Yep, should have 2, one at negative 1 over root 2 and the other at positive 1 over root 2. So let me get myself another page here. We need to find f of negative 1 over root 2, and we need to find f of 1 over root 2. And our original function was what? E to the negative x squared, right? So these should come out to be the same, right? Because if I square negative 1 over root 2 and positive 1 over root 2, I get the same number. I just get a half for both of those. So this just becomes e to the negative 1/2. Or let's say 1 over root e. And so our points of inflection are negative 1 over root 2, comma 1 over root e, and 1 over root 2, comma 1 over root e. And if we weren't asked to, but if we were asked to indicate when it was concave up and concave down, we would say it's concave up from negative infinity, right? Negative infinity to negative 1 over root 2 union 1 over root 2 to infinity. And we would say down, concave down from negative 1 over root 2 to 1 over root 2. Good or no?
And these are still parentheses on the real numbers?
Yep.
Okay.
Yeah, for the concavity, it's always parentheses. No matter what, it's always parentheses. For the increasing and decreasing on infinities, you still use parentheses. But if the point is defined on the function, the College Board wants you to use a bracket. So.
Got it. Thank you.
Somebody had asked me, I think it was Ian, right? I think you asked me about this. That what if the point for the increasing and decreasing intervals, it's a real number, but the point's not actually defined on the function because there's a discontinuity or something. Yeah, you would still use parentheses because the point's not even defined. So if the point is defined, then you got to use the bracket for increasing and decreasing. But for concavity, it is always parentheses. Everybody good?
Yeah.
All right, maybe we should take a look, maybe just for fun here, at e to the negative x squared. And so there it is. And what were our values? It was x was negative 1 over root 2, right? And x equals 1 over root 2, just so we can see where the change in concave, these are our points of inflection, right where these two lines intersect. Right? So we can see it's concave up, it's following this, even though it's doesn't look like it's really increasing much here for a long time. It still is, just ever so slightly. And then it's concave up, and then right here it flips to concave down, and then right here it flips back to concave up. Good or no?
Good.
All right. So now we want to note a couple of things. First off, similar to like our increasing and decreasing and maxima and minima, where the first derivative might have been 0, we might have had a critical value, but we didn't necessarily have a max or a min. Well, the same thing can be true with the second derivative. The second derivative could be 0 at a non-inflection point. So if we take something like x to the 4th, just to illustrate this real quick, its derivative is 4x cubed, and its second derivative is 12x squared, which equals 0 at x equals 0, right? True? Everybody agree there?
Yeah.
Great. So if I plug in something more than 0, like 7, 12 times 7 squared is positive, concave up. Plug in something less than 0, like -7. 12 times -7 squared is also positive. So there's no change in concavity. So we have to make sure that we don't just say, oh, the second derivative was 0, must be a point of inflection, because no, not necessarily. You have to check for this sign change. And if we go in and we look at x to the 4th, we should know what x to the 4th looks like, but there's x to the 4th, right? It's just this quartic function. It's got a local minimum at 0, but it doesn't have a point of inflection at 0, right? And also, we want to make sure that we do look for places where the second derivative doesn't exist. So if we're looking at f of x equals the cube root of x, like x to the 1/3, then f prime would be 1/3 x to the -2/3, and f double prime would be -2/9 x to the -5/3, or -2 over 9x to the 5/3, which is undefined at x equals 0, right? So we got to make sure we check for these values where it's undefined. We plug in a positive to this, right? 9x to the 5/3, a positive number. This denominator is still positive, and so it becomes a negative when you do -2 divided by it. And if you plug in a negative number, right? 9x to the 5/3 with a negative number, well, cube root of negative, it's still negative, and raise a negative to the 5th power, it's still negative, and multiply it by 9, it's still negative, and your negative divided by your negative gives you a positive. So you have to check for the points where the second derivative is undefined. And this is cube root of x, right, which we should be relatively familiar with since we looked at it the other day. X to the 1/3, right? It's concave up. And then it switches at this vertical tangent line. It switches and has a point of inflection and becomes concave down. Good or no?
Good.
Wonderful. All right. How is everybody feeling about all of this? Are we feeling okay? Feeling like we could do this?
Feeling fine.
Oh, good. All right. Now, we're going to add in one last little test here. This last little test is called the second derivative test for local extrema. So everything we did before with the second derivative was talking about concavity and points of inflection. But the second derivative test can also help us at critical values to determine if we have a maximum or a minimum. And so before we even get started with this, I want to caution you about it, that this second derivative test only works if the derivative is 0 at some value c. It doesn't work if the derivative is undefined at c. It only works if the derivative is 0 at c. Okay? So if the derivative is 0 at some value of c, then you can take the second derivative and you can see if it is positive or negative, and that will tell you if it's a maximum or minimum at c. So a second derivative being negative tells you a maximum at c, and a second derivative being positive tells you a minimum at c, as long as the first derivative was 0. So let's just think about this without really doing a bunch of work. Let's think about a function that has a second derivative that is positive, like x squared, right? That's a function that's concave up, right? F double prime is less than 0. Would you agree with that? Oh, sorry, F double prime is greater than 0. Sorry, you shouldn't have agreed with what I just said. F double prime is greater than 0. It's concave up, right?
Yes.
Okay, so if we took the critical value, let's say this was f of x equals x squared. What's the critical value of f of x equals x squared?
0.
Should be x equals 0. Well, at x equals 0, what is the second derivative's value? We know f double prime of x is 2, right? Second derivative's value is positive, telling us this is concave up. So at this critical value, we know that we have a local minimum according to our rule. And what tells us that is the fact that the function is concave up, right? If I have a concave up function, there is no way for us to have a local maximum on a function that's concave up. And there's no way here for us to have a local minimum on a function that's concave down, as long as the derivative is defined at that point. Right, so I could have a function that was concave down on both sides, right? This is concave down and concave down coming to a cusp, right? And I have a minimum there, right? But I can't do that in a place where the derivative is 0. This is a place where the derivative is undefined. Does that make sense?
Yes.
Wonderful. All right, so we're going to use this test to try and work out the extrema of this function, x cubed minus 12x minus 5. So let's find our critical values first. How do we find our critical values?
Find the first derivative and then set it to 0.
All right, find our first derivative. What's f prime?
3x squared minus 12.
And set it equal to 0 and see when it's undefined, right? Never undefined, but when does it equal 0? At x equals
2.
and
-2.
positive or negative 2, right? So we could make a sign chart, but we're going to use the second derivative test. The second derivative is 6x. So tell me what 6x is evaluated at x equals 2. Should be
12.
12, which is greater than 0, which tells us that there is a minimum at x equals 2. And if we evaluate it at -2, that's -12, which is less than 0, which tells us that we have a maximum at x equals -2. And if we were to do the sign chart, we could use the sign chart just to check our work if we wanted to. But remember, we did this one before. If we plug in something in between like 0 to our derivative, we get negative. And if we plug in something greater than 2, like 1,000 to our derivative, we get positive. And also we get positive over here, which would tell us increasing to decreasing to increasing, or a local max at -2 and a local min at 2. Does that make sense?
Yeah.
Any questions? Everybody okay? All right. So here's what we're now going to do. We're going to take some random function that you probably don't know what the graph of it is, and we are going to, first off, find X and Y-intercepts, which should be easy enough because you should have learned how to do that years and years ago. And then we're going to use our first and second derivative tests to determine when the function increases and decreases, when it has local maxima and minima, when it's concave up, when it's concave down, and where its points of inflection are. And then from there, we're going to try to sketch ourselves a really nice looking graph of it that we might not be able to do without all this fun calculus stuff. Sound good?
Yeah.
All right. So we'll start off with the X and the Y-intercepts. So how do we find that? We can do that by setting it equal to 0, right? At least to find the X-intercepts. And what do we get?
X equals 0 and X equals 2.
All right, so we got 2 X-intercepts, 0 and 2. I'm gonna say that each 2 squares here is 1 unit for us here. All right. How many Y-intercepts can a function have?
1.
1. So we've already got 1, right? It's 0, so we don't need to bother looking for a Y-intercept. So now what we'll do is we'll find a first derivative. So what's our first derivative here? What's our-
4x cubed minus 6x squared.
All right, 4x cubed minus 6x squared. So real quickly, you guys factor that out and solve for when it equals 0 and when it's undefined. What'd you factor out?
2x squared.
2x squared times a 2x minus 3. So that should have given us x equals 0 and x equals 3/2. And we would know that our function's derivative was never undefined, right? Okay, so we're going to want to make a sign chart with these values, 0 and 3/2, to just see what's happening with our function. If we plug in something that is negative to this, the negative squared is positive. So this outside term is positive. And I plug in negative 1,000, let's say. This inside term in the parentheses is going to be negative, right? Which means we should be decreasing because our derivative is negative, from negative infinity to 0. True? Okay. What if we plug in something between 0 and 3/2, like 1? Well, 2 times 1 squared is positive, right? And 2 times 1 is 2, minus 3 is negative 1. So we're still negative in here. So we're actually still decreasing from 0 to 3/2. So 0 is not a max or a min, right? And then we plug in something more than 3/2, like 1,000,000, positive and positive. So now we are decreasing. And it would appear that the point at 0 is not maybe super important to us yet, but we've already got it plotted, so that's good. And then we also are going to need the point at 3/2. That's an important point, right? That's a local minimum. So we're definitely going to want to plot that one. So f of 3/2 is what? That's 3/2 to the 4th power minus 2 times 3/2 to the 3rd power. What does that come out to be? 81/16, right? Minus 54/8, which is what? Negative 27/16. Hopefully my arithmetic's right on that. You guys agree with that or no?
Sure.
Oh, that sounds like confidence there. All right. So negative 27/16, that's a little bit less than negative 1.5. So 1.5, we're a little bit less than 1.5. Something like there. Everybody okay with that?
Yes.
All right. Now we need a second derivative. So our first derivative was 4x cubed minus 6x squared. So what's our second derivative?
$12x squared minus 12x.
Wonderful. Is that ever going to be undefined?
No.
Nope. So we'll look at when it's equal to 0. And so 12x times x minus 1, which gives us x equals 0 and x equals 1. Good or no?
Good.
All right. So we'll make a sign chart, 0 and 1, and plug in some values in between. So less than 0, a negative value, right? That's going to give us a negative here and a negative here. So a negative times a negative should give us a positive. And between 0 and 1, like a half ought to give us a positive and then a negative. So negative. And something greater than 1,000 should be positive and positive. So it looks like we have how many points of inflection? Looks like we have 2 points of inflection, right? One at 0, which we already knew the point for 0. It's already plotted. So now that's kind of an important point because it's a point of inflection. And we have another point of inflection at x equals 1. And so we need to figure out what's f of 1 for our point of inflection. So
-1.
looks like it should be -1. Yep. So 1, -1. And now it may not seem like we're ready to plot or to graph this. We've only got 4 points plotted, but I think we have enough information. So we know, just on our basic knowledge of 4th degree functions, if the a value in front of the x to the 4th is 1, it's going to look like this in some degree, right? It's going to be going up to infinity, both to the left and to the right. So we know we're starting up here, and we are decreasing all the way to 3/2. But what happens at 0? At 0, we have a change in concavity from concave up to concave down. So at 0, we need to do something like this, don't we? To continue decreasing and change from concave up to concave down. Probably not real well. Not real well. That still looks pretty bad, but we're going to pretend like it's good. And then what happens from 1 to 3/2? Well, it's still decreasing, but after 1, it switches to being concave up again. So really, we've got to go here and now switch. That doesn't look good. Switch to concave up, and then we hit this local minimum and curve back up and stay concave up. And that's, if I could draw better, a pretty good representation of what that graph looks like. Anybody have any questions on that? We feel okay about that. It's concave up from -infinity to 0, right? According to short chart. Then it's concave down from 0 to 1. Then it's concave up again from 1 to infinity. So it meets all the concavity criteria. And then it's decreasing from -infinity to 3/2. And then it's increasing from 3/2 to infinity. x to the fourth minus 2x cubed, right? I know this looks so much nicer than mine did, but same basic idea, right? We're concave up and decreasing, concave down and decreasing, concave up and decreasing, concave up and increasing. Any questions on that, or is everybody okay with that, or?
We're good.
All right. Sure is silent out there. All right, let's do another one. This one you definitely don't know what it looks like right off the bat. Do you want to try and work on this one on your own a little bit, or do you want to just work through it together?
Find the derivative.
Yes, but the question was, do you guys want to work on it together, or
Oh,
do
I
you want to
didn't.
work on it on your own?
Together, please. That is
Together, all right. Sorry, Max, you don't get to make the choice. Go back to your class. All right, we'll work together on this one. So first off, let's find the x-intercepts, yeah? Set it equal to 0. When is the cube root of x squared equal to 0? When x is 0. And then what about this? This should be 2 cube roots of x equals 3. Or cube root of x equals 3/2, or x equals 27/8. So that's about 3 3/8. Well, it's exactly 3 3/8. And then at 0, 0. So we got 2 x-intercepts. Everybody good with that?
Yes.
Cool. All right, now time for a first derivative. So we have two options here. One option is to take the derivative as is. The other option is to distribute that x to the 2/3 through first and then take the derivative. I would normally ask if anybody has a preference on that, but I'm not going to ask. I prefer to distribute the x to the 2/3 through. So that gives us f of x equals 3x to the 2/3, right? And then minus 2, and we've got x to the 1/3 times x to the 2/3, which is just x. And so now this is a much easier derivative to take. True?
Yes.
Yeah.
All right, so we got f prime of x is equal to what? 2x to the negative 1/3 minus 2. Yeah? Or 2 over the cube root of x minus 2. So when is this undefined?
At x equals 0.
At x equals 0, so there's one critical value. And when does this equal 0? Well, that'd be if 2 over the cube root of x minus 2 equals 0, or 2 over the cube root of x equaled 2. Well, what would, no, this is a 1, right? What would, that would mean that the cube root of x equaled 1, which would mean that x equaled, well, what x have to be? Yeah, it'd have to be 1. So we got two critical values, x equals 0 and x equals 1. We'll make ourselves a sign chart with 0 and 1. Plug in a negative number, like negative 1,000,000, right? If I plug in, doesn't even matter what negative I plug in here. This number here is going to be a negative, right? Any negative number that I plug in, cube root of x will be negative. Yes, Mr. Bachelor, if I cube root a negative, it is a negative. And then when I do 2 divided by that negative, it's still negative. And when I subtract 2, it's still negative. So decreasing. If I plug in something between 0 and 1, like let's say a half, or let's say something easier to cube root, like an eighth. What's the cube root of an eighth?
1/2.
1/2, and 2 divided by a half is 4, right? 4 minus 2 is 2, so positive. And if you plug in something more than 1, like 1,000, the cube root of 1,000 is 10. 2/10 or 1/5 minus 2 is negative. So our function is decreasing from negative infinity to 0, and then increasing from 0 to 1, and then decreasing again from 1 to infinity. Good or no?
Good.
All right. Now what do we need to do? We need to do a second derivative. And we also probably need to figure out what the value at x equals 1 is. Maybe we should find out f of 1 while we're still on this page. I'm sort of out of room here. We'll just find f of 1 right here. F of 1 ought to be 3 minus 2, right? Which is just 1. So should be able to go in and plot the point at 1, 1. Good?
Good.
All right, now we'll take our second derivative. So our first derivative was 2x to the negative 1/3 minus 2. So what should that give us for our second derivative? The derivative of 2x to the negative 1/3 ought to be negative 2/3 x to the
Negative 4/3.
4/3, and then the minus 2 should be just 0. So we could rewrite this as negative 2 over 3x to the 4/3. Is that ever equal to 0?
No.
How can a fraction equal 0? Only if the numerator is 0, right?
Correct.
So this fraction can never equal 0, but it could be undefined at x equals
0.
0. So we'll make a sign chart with 0, even though, are we going to have a point of inflection there? Well, let's just see. All right, let's plug in a positive. If I plug in a positive number, I cube root the positive, that's positive. I raise it to the 4th, that's positive. I multiply it by 3, that's positive. I do 2 divided by it, that's positive. And there's a negative, so negative. And if I take a negative number and I cube root that negative, I get a negative. And then I raise that to the 4th power, I get a positive. Times 3 is positive. 2 divided by that is positive, and then there's a negative. Right, so there's no point of inflection, no change in concavity. This is always concave down. And we should have been clued in that there wasn't going to be a point of inflection at 0, because we already knew that we had a local minimum at 0, right? And if you have a local max or a local min somewhere, you can't also have a point of inflection at that same x value. So we've got enough information now to graph this. We know it's always concave down. And we know that we've got a function that decreases, then increases, then decreases, but has to stay concave down. So here is this piece that's concave down. And then it starts increasing again from 0 to 1, and then starts decreasing again at 1, but it has to be concave down. So it's going to look something like that. And we should have been clued in that this point at 0, 0 wasn't going to be a nice smooth local minimum, because we got that local minimum from a place where the derivative was undefined. And that's exactly what we have here, is we have a cusp at this place where a derivative was undefined at x equals 0. And then we had a nice smooth local max at x equals 1, because that came from the derivative being 0. Good or no?
Good.
Great. And just to verify our work here, we could take a look at it in Desmos and see an even nicer looking version. What was it? X to the 2/3 times. What was the other part of it? 3 minus 2x to the 1/3. And you'll note that it looks just like what we drew, doesn't it? Yes, it does, Mr. Batchelor. It looks just like what we drew. That's so amazing. It's amazing how we can use calculus to take a function that we knew nothing about and get a very, very accurate graph of it. I am astounded and amazed, right? That's what you're all thinking?
It looks beautiful.
Oh, wonderful. That's great. All right. We are going to stop there for today.